Hello, my name is Brian, and I'm introducing our paper on optimal transport couplings of Gibbs samplers on partitions for unbiased estimation. And this is joint work with my equal co-author, Tin, as well as our advisor, Tamara. So several key unsupervised learning problems reduce to inference over partition. For example, in text modeling, we use latent Dirichlet allocation to assign words in different documents to different topics. And in biology, we use Bayesian nonparametric clustering to assign cells into different cell types based on the genes that they express. Additionally, for community detection, we use stochastic block models to assign users in a network into different communities. For all of these problems, Gibbs sampling or collapsed Gibbs sampling is a gold standard for accurate inference. And inference with this approach essentially reduces to repeatedly cycling through all of the data points and relabeling them into different groups. However, this suffers from the age-old problem that MCMC can take a really long time. And the goal of this work is to try to reduce the wall time required by utilizing parallelism. So to line up the technical problem that we solve, I'm going to first introduce some notation. So we're going to let X be a partition of the data. So for example, if we have 3 data points, this could be the set 1 and 3, as well as just the set 2. And we're going to take a Bayesian approach and model this unknown partition as random with some distribution pi, which for these examples might be the posterior distribution, say, after we see the edges in the network or the expression levels of each cell. And we typically don't care about all of pi, but rather a few expectations with respect to pi, which I'll write as E of h of x. And since we don't have direct access to pi, we're going to use MCMC to compute these. However, this will have the problem of burn-in bias, which I'll explain a little bit here. So if we have this Markov chain, which I'll write as x0, x1, and on, converging to pi in distribution, then we might think of using some finite time like xt's to estimate these expectations. However, for any t less than infinity, expectations computed in this way are not actually going to be equal to the target. And as a result, parallelism gives us very little help. So even if we average across multiple chains, we're not going to get rid of this burn-in bias. To approach this problem, we use computational couplings following the framework of Pierre Jacob and his co-authors from 2020. I'll give a brief overview of that approach here. So we construct a second coupled chain, which I'll write as y, which is equal in distribution to x, and has this property that it becomes exactly equal to x. It meets x for all t after some meeting time tau, with an offset of 1. And if we have this, then it turns out that this expression in blue turns out to be an unbiased estimate of our target expectation. And the power of this is that we can compute many of these unbiased estimates in parallel and average them to get an arbitrarily accurate estimate. So the problem that we're approaching in this work is how to deal with this heavy dependence of this approach on the particular method of coupling these chains x and y, which needs these chains to meet in a small time. So we approach this question of providing small meeting times tau for Gibbs samplers that work on partitions.
Hi, my name is Tin. I will first walk you through our methodology. The idea is to construct transition kernels T star so that the next value of x and y are close. Idea being, if the distance between the two monotonically decrease, then the meeting time between them must be small. Algorithmically, each of the samplers change the label assignment. For instance, before the transition, data points 1 and 2 had label 0, while data point 3 has label 1. After, the labels of 1 and 3 remain the same, but data point 2 now has label 1. Conceptually, the samplers have transitioned from one partition to another. In the same example, before the transition, 1 and 2 were their cluster, 3 is its own cluster. But afterwards, 1 is its own cluster, while 2 and 3 are a new cluster. We take the conceptual view and then compute optimal transport couplings between the distribution over the partition. We first pick a distance d between the partitions. Next, we compute T star as the coupling that minimizes the expected distance between the next states. The marginals are discrete, so we could solve a linear program to find this T star. Finally, we provide experimental evidence backing the coupling and the benefits of estimation. Our coupling is compared to 2 alternatives that only use label assignments, so they are subject to label switching problem, where a lot of label assignments correspond to the same partition. On the left, we see that the distance between the 2 chains decrease stochastically at a faster rate to 0 for our coupling compared to the alternatives. On the right, we're plotting the histogram of the meeting time for the different couplings. Again, under our coupling, the meeting time generally is smaller than the alternatives. Finally, we show the definite benefits of unbiasedness. Recall that we wanted to estimate integrals of target distributions. Here, the ground truth is obtained from a very long Markov chain, whereas the red is obtained from a single Markov chain, and the blue is our coupled estimate. Even in the limit of a lot of replicates on the x-axis, the bias of the red precludes error from going to 0, whereas because our blue estimates are unbiased, having a lot of replicates drive the squared error to 0. Thank you for your attention. The next slide has references for further reading.